Welcome back. And the topic this week is to try to wrap up this discussion of the link between the time-dependent formulation of many-body perturbation theory and the time-independent formulation which we looked at. Yesterday, we also went through the setup of the Wick's time-dependent theorem, which is an extension of the time-independent one. And this is something which will be very useful when we start looking at Green's functions. So as you will see today, a Green's function contains essentially all the information about how a many-body system evolves in time. So if you can calculate the Green's function, or what is normally called the propagator, or the resolvent, so there are many different names for the same quantity, then you have essentially all the information which is needed for how a system propagates in time. This is extremely useful, and it's a formalism which also lends itself to a direct comparison or direct interpretation of experimental observables. So compared to many-body theories like perturbation theory or copper cluster theory, which we haven't discussed, it's often a little bit more involved to calculate expectation values beyond the ground state energies. With Green's functions, we can actually calculate many of these quantities if we have the Green's functions. So I should, in a way, also try to moderate this optimism about the Green's functions, because obtaining the Green's functions is the same as having the exact solution to a many-body problem. So that means that we need to do approximations. And the approximations which are typically done is the resummation of specific terms in many-body perturbation theory. So we will see many-body perturbation theory applied to Green's function theory as well. And then the different approximations, however, are much more powerful because they lend themselves to an easy connection with experimental data. So let's, however, try to wrap up what we discussed yesterday. So I'm going to switch to the whiteboard. And let's try to do that as soon as possible. So this is just going to take some few minutes now, and then we are going to switch over to the theory of Green's functions. So what we had yesterday was a calculation of the correlation energy, which we had defined in terms of this time evolution operator, which is a unitary transformation. And if we obviously have the time evolution operator, we have in essence solved the many-body problem. So this delta E was given as a limit, and we use this adiabatic hypothesis, where this goes to 0, along from the positive side. So we have a phi, which is the unperturbed energy. We have the interaction piece, and this is multiplied with this operator, where the interaction now depends on this parameter alpha. So we switch on the interaction, and then at time t equals 0, we can think of the system as being fully interacting. And we have a solution at time minus infinity, which is given by the non-interacting case, or the unperturbed case, as we called it. And this is then given by this ratio. And this is a ratio which you can show contains only so-called link diagrams, where all the vertices are connected by at least one fermion line. Then what we showed yesterday is that we can rewrite this as a lim of alpha goes to 0, and in terms of a log, so dt of log, and then we had the expectation value of phi 0 of u of alpha, and t minus infinity phi 0. And this is evaluated at time t equals 0. So that's where we perform the evaluation, because that's the fully interacting case. So the assumption here with the adiabatic hypothesis is that the switching on of the interaction evolves adiabatically, slowly, and that we can start with a system which is non-interacting. So we have the exact solution in the time limit of t minus infinity. And then what we did yesterday was actually to rewrite this quantity, phi 0, of u of alpha 0 minus infinity of phi 0, we just rewrote that in terms of the different operators, order by order. So we are doing an order by order expansion of the time evolution operator. And this was given by u of n. So let me just rewrite that one. Sorry. This is a u of n of phi 0. And when we took the log of that quantity, we actually rewrote that one in terms of, let's just rewrite this one. So this is an n equal 1 to infinity of an an. And where this an is now simply phi 0. And this has a u of n. And u of n is the interaction at a given, is the operator with the interaction at a given order. So if n is equal to 2, then the interaction appears twice. So that would be a second order term for the evolution of the wave operator, or this unitary transformation. And then we took the log of that quantity. So when we take the log of this quantity here, we can rewrite that one. So let's just rewrite this t minus infinity. Let's just put it in a more general term. Then this is something which we can rewrite as a sum over these a's. So I'm just Taylor expanding now, minus 1/2, and then I have a sum over an squared, and then plus 1/3, and then a sum over an cubed, and this goes on plus minus to infinity. And this would be the same when we write it out as an a1 plus an a2 plus an a3 plus, and then I have minus 1/2 a1 squared minus a1 a2 and plus 1/3 a1 cubed, etc. So what is common to do then, when we are looking at, as we did previously, we rewrote then delta E, the energy, in terms of delta E to first order, which was nothing but phi 0 of h of I of phi 0. And then we had second order, and this goes on to infinite order in the interaction. So let's see if we can make a link between the expression here with the time evolution operator acting on the state and what we developed earlier with the time-independent Rayleigh-Schrödinger perturbation theory. And I'm just going to show you one of the recipes by which you would do that, because what we need now, if we look at delta E to first order, that is going to be given by the limit of alpha goes to 0. And then we have I, and this is given by the derivative of A1 with respect to time. And this is evaluated at the time t equal to 0. If I do delta E2 here, that is going to have a similar limit. Alpha goes to 0 of I, but then I have to take the time derivative with respect to A2 minus 1/2 of A1 squared. Now, the latter term is actually going to disappear because it will give rise to unlinked diagrams in that specific case. And so the terms like an A1 times an A1 will give rise to so-called unlinked diagrams. And you can actually show when you run the calculations of these terms that the last one will disappear, and you will only be left with this A2 term, which is the same which we evaluated earlier in time-independent perturbation theory. So let's look at the first one, because then we can, so if we take A1, so A1 is nothing but the expectation value of phi 0 with a wave operator acting at first order at phi 0. And this is equal to phi 0. And now I'm plugging in this expression which I have for the wave operator. So this is a minus I. And then we have an integral from minus infinity up to a time t. And then we have the interaction at a time t1. And then we have the integral dt1 here. And this is acting on phi 0. So this is the expression for this specific quantity. Now, when I now take the derivative of that quantity, so what I have then is a dA1 with respect to time. And the only quantity here, which,
is this the same as when you do QT, the spatial exponential?
Yes, exactly. So the wave operator, which we discussed last week and also yesterday, is the same as you would have in QFT. It's exactly the same. There is no difference. Except that now you have this time order product, which you will also have in QFT. So when you introduce Green's functions, which in a way is a little bit more complicated to solve as a many-body type of method, because you have the time dependence, then what you have is a direct link with quantum field theory. So for those of you who have taken a course in quantum field theory, you can just make a one-to-one correspondence, except that now you don't deal with the Dirac spin-offs or with the solution to the Klein-Gordon equation, but you have simply a spin-off or a non-relativistic solution of Schrödinger's equation or non-relativistic quantum mechanics. But essentially, the machinery is exactly the same. So this would be a typical first-order contributions in quantum field theory. So if you're doing QED, this could be the first expression which you have, which I never remember the name, whether that's a Thomson scattering. If you are looking at the, so what's the name you have? When you do the second order term, then you can have electron-electron scattering, positron-positron scattering. You have this Möller process, the Baba scattering, etc., etc. And but there's one for the first order term, which then would be the scattering by an electromagnetic field, for instance. And it has a specific name. I never remember that name. You probably have seen the equation for the first order term. There is a name. Every one of these terms has a name. So if you want your name in physics, you have to cook up a 10-folded diagram and then have a special physical process, and then maybe you can get your name on it. You probably heard in particle physics, there's a set of diagrams which are called penguin diagrams. And there was actually a party at CERN where they had a bet that John Ellis, in the next paper he should write, he should have the name of an animal for the diagrams. And then he came up with a diagram which looks like a penguin. And these are the penguin diagrams. Just some gossip here. Now, if you take the derivative here, you see immediately that this one is equal to minus I, and then you have phi 0, and then h of I of t of phi 0. So this is pretty straightforward to do, actually. And that means that when I take now the expectation value at time t equal to 0, so when I'm setting up d of a1 at dt, and then time t equals 0, then what we end up with is minus I, and then I have a phi 0 of hi at time 0 and phi 0. And this is nothing but minus I, and then I have phi 0. And this is my Hamiltonian at phi 0. Because this h of I, when I had it plugged in the time dependence, this was actually given by h of I times e of alpha of t. So I'm taking the limit where alpha goes to 0, and then I'm taking the time at time t equals 0, and t equals 0 is the same as the time-independent Hamiltonian. And we have assumed that the Hamiltonian does not depend on time. That's a basic assumption we made here. And then that simply means that delta E1 is equal to, when I now remember that I have an I here, so it's I times a minus I plus 1. So this is simply equal to phi 0 of h of I of phi 0. And this is what we've seen before for the first order contribution from time-independent perturbation theory. And then we can go through a similar exercise and look at the time derivative of this term A2 and also the time derivative of the term A1 squared. And when you do that, you will actually see that this last term disappears, and we're only left with this term, and that is the term which will give rise to the standard second order perturbation theory term. And then if you are particularly eager to calculate derivatives, and this is a kind of a passion you have, or when you like to do that in the evening in your spare time, then you could try to do this for third order, fourth order, and so on. But in essence, what we have is a direct link with the many-body perturbation theory. So the topic which I wanted to do now, after we had this small digression, is now to use a time-dependent formalism to introduce Green's functions, and Green's functions as a many-body theory. And in particular, what we are going to look at is something like the solution of Dyson's equation, which is a very important tool in the calculation of Green's functions. We're also going to see how we can link the Green's functions with calculations of properties like observables like the energy and other properties of or other specific expectation values. And the Green's functions provide a very powerful mechanism for that. But let's just introduce the single particle Green's function first. So let's start with the Green's functions, single particle Green's function. And there are many ways to derive what I'm going to show you now. And I'm going to show you two specific ways by which we can derive it. Single particle Green's function. So the formalism is not that intimidating, but let's start now with a system where we have the Schrödinger's equation, and we are acting with a Hamiltonian on a specific state, and this state is an alpha of t0. So we have we can rewrite this as an H acting on a. We write this in a more compact way. So this is the system in a given state, alpha. We are not looking now at the spatial degrees of freedom. We are just looking at the specific quantum numbers the system can be in at a given time t0. So t0 could be the time which we put in to be equal to 0, or it could be minus infinity if we want to, just any given time. And we know that the solution to this problem here, if these are eigen, we are assuming now that these are eigen states of H. So this is a single particle problem, the way we are starting it now. So think of this as a single particle Hamiltonian. So this is a one-body Hamiltonian, H, and this is just a one-body state. And we're assuming that this one is now given by some eigenstate, an alpha at a time t0. And we know that this equation here is also a solution to Schrödinger's equation. So I'm not introducing these pictures which we had earlier. So this would be given by H acting on this alpha at time t. Okay. Now I can now define the full wave function, which also includes the spatial degrees of freedom. And we have seen earlier that psi of alpha of r of t, like this, is something which is given by this overlap of r and then alpha of t. Okay, so these are just basic definitions which you probably have seen before. And we know that this one is something which we can rewrite in terms of r, and then we have e of minus I of h divided by h bar of t minus t0. And now I'm using the properties of the wave operator and expressing that through the integration of the equation we have here. And we are still in the Schrödinger picture. When we are going to dive into the explicit setup of Green's functions, we are then going to go into the Heisenberg formalism and not the interaction formalism. And you will see why a little bit later, why the Heisenberg picture is the more relevant one. But here, we are just using the standard Schrödinger formalism. And this is now the wave operator acting on, through this unitary transformation, on the wave function at the time t0. And we are assuming now that we know this solution here. This is something which we can calculate, and we know that. So we're just looking at the time evolution of this quantity. I hope everything is fine here. So these are just basic definitions. And then what we can do now when we are calculating this one, we can now insert a complete basis. So insert a complete basis. And this complete basis is we have the completeness relation, which we can use then. So that means that I can now write the state alpha of R of t, which is now given as an integral over, I'm using the completeness relation over R. I assume that you've seen this in some of the more basic quantum mechanics courses. So we have R, and then I have my E of minus I divided by H bar, H of t minus t0. And then I have R prime. And this is multiplied with R prime. And then I have the state alpha of t0 at t0. Okay. And I know that this quantity here is nothing that this psi of alpha, which we know the solution to, of R at time t0. So this is something which we can solve at a time t0. It could be a case where we have the unperturbed solution where there's no interaction, and then we would switch gradually on the interaction. And then we just simply assume that this is something which we know. And I can rewrite this equation here now in terms of a new quantity, which is going to be given by H times I times H bar. And then I have my D of R prime. And then I have my Green's function. And then I have the distance t minus t0 multiplied with this psi of alpha of R at t0. So this is just one way by which we can look at this one. And this G, which we have here, is this G, which is a function of R and R prime. Often it's just a function of the relative distance. Now it's also a function of the time difference. This is given by minus I divided by H multiplied with this quantity which we have here, which is an overlap involving the time evolution operator of t minus t0 multiplied with R prime. So this expresses all the kind of physical processes when moving from R prime to R. And it represents the way the system propagates through space here. So this is the way you can look at it. In a sense, this is a transition probability, which you're having. And it represents the transition probability for moving from a state with R prime to a state with R. So in a new position, in a time distance t minus t0. So in a certain sense, if you recall back Huygens' principle, this is something which mimics that principle in wave mechanics. You have a question here. Yes, you're right. That should be an R prime here. So that should have an R prime. Sorry for that. I just forgot that. That should be an R prime here. Excellent. So the way you interpret this is actually as a transition probability, and it represents all the multitude of transitions which you can make from one position to another one. And then you're integrating over all the positions the particle can be in, and then you end in a specific final position. This forms the basis for a lot of all of the wave mechanics, the basis for Markov chain theories, etc., etc., etc. So this kind of interpretation in terms of a Green's function is something which you will see again in many different applications in the natural sciences. So I read this as a transition probability. It defines, or the way the system propagates through space in this specific case, and it has an explicit time dependence and an explicit position dependence. Yeah.
Given that this is a distribution, did you estimate this with Monte Carlo methods?
Oh yeah. So people actually do that. And for those of you who have studied methods like variational Monte Carlo methods, it's pretty common then to use an estimate for the Green's functions to say how the particles are jumping in space with a given probability. So for those of you who have taken a course like Computational Physics 2, which is essentially a course on variational Monte Carlo methods, you will see ways to approximate this Green's function, which represents a transition probabilities in the theory of Markov chains. So you are going to encounter these again and again. Now, the thing which is important for us is that if you know this function, if you know G, then you essentially know everything about the system. So we have the initial solution, which is set, this psi of alpha at the time t0. If we know that one and the Green's function, then we can actually say everything about how the solution is going to propagate and develop through all times. So it's an extremely powerful, I mean, in this kind of compact expression here, this is an extremely powerful set of statements which you can make about a physical system. Now, this is in a way the basis. There are several ways by which you can also rewrite this equation. So let's look at alternative ways here. And some of these are more handy when we are doing many-body physics. Alternatives to the above derivation. So let me just set that up. Because later we are going to introduce a discretized variant of this. And this discretized variance is something which is called a Lehmann representation. And this is something which we are going to look at a little bit more later. So what we are going to assume then is that we have H and acting on a state n, and that gives us an epsilon n as a function of n here. So these are the exact eigenstates. So just keep in mind that what we did previously assumes that we know the exact eigenstates. In general, we don't have that. And that's where this unitary operator, which we call the wave operator, or the time evolution operator, comes in, and where we're going to make perturbative approximations. Because in principle, we don't have the exact solution. So these are the exact solutions, and we are still staying with a one-body system. So these are the exact solutions to the problem. And what I'm going to use now is more a formalism which now involves second quantization. So I have an R prime, and then T minus T0. And this is going to be equal to minus I divided by H bar. And now I'm looking at the state in the true vacuum. So this has an R. And then what we have then is the E to the minus E divided by H bar of H of T minus T0. And then I have my A of R dagger acting on the vacuum state. Then what I'm going to do then is to set in a complete set of states. So this is going to be given by minus H, and then I have a complete set of states N, which are the eigensolutions to the Hamiltonian problem. So this has an A of R of N, and then it contains an N of A of R prime, dagger, acting on 0. So I create a particle in a position R, and then I excite this to a state N. So this is a new state N. So this is just the overlap from you having created a particle with momentum R. And then you take the overlap with this intermediate state N, and then you de-excite it, and then you're back to the vacuum state. And this is multiplied since we now have this term here, this H is now going to act on these intermediate states. And when we do the Taylor expansion of the exponential, this is nothing but us having an e to the minus I divided by h. And then we have the eigenvalues, epsilon n of t minus t0. And it's common then to rewrite this in a slightly more compact way. So we could now rewrite this as a h, and then I have a sum over n. And now I'm simply going to call these for us function un of r. So I'm going to have a function un of r, and then I have a un complex conjugate of r prime. And this is multiplied by this propagator, but by this exponential of epsilon n of t minus t0. Now, there is a very important thing here. And as we discussed when we looked at the Wick's theorem with time dependence, so we have to obey causality. We need to have t larger than t0 or equal to t0, because else it doesn't make sense. We have something which happens at t0 and then we propagate through time, so t has to be larger or equal to t0. And this is simply to obey causality. So this brings us back a little bit to what we discussed yesterday with Wick's time-dependent theorem. And what is often done then, if you look at this equation which you have here, is to perform a Fourier transformation. This is the standard approach which is often used in Green's function theories, because with the Fourier transformations, we have often a simpler representation in terms of the way we are going to do the computations. So what we are going to do now is to consider the, and one way to actually introduce this time causality is to introduce a theta function. So to include causality, then a practical way of doing that is to introduce a theta function. We introduce theta. So the theta function, the step function, minus t0. And we are going to perform a Fourier transform. And to perform a Fourier transform, which I will shorten to FT. So when you see this acronym FT, that's a Fourier transform. What I need is an equation for the theta function. We need this theta of t minus t0, which is equal to minus 1 of 2 pi of I. And then I have an integral over the energies. So I'm Fourier transforming time into energies. Okay? So this is the equivalent of dealing with the time dependence. We're just Fourier transforming, and then we have the energy dependence. If you're dealing with the coordinate degrees of freedom, when you Fourier transform them, you transform into momentum space, right? So now we're just looking at the Fourier transform of time by introducing this theta function, which is a practical way of including the causality. And then this is going now to have an e of minus I divided by h bar. There's going to be an e of t, this is an e prime, t minus t0, divided by this e prime plus a parameter I eta. So this I eta is something which we're going to let to go to 0 from the positive side. This is implied here. And for t larger than t0, then we can perform the integration of this quantity here by closing the lower half plane. So now I'm just calling back or trying to reboot some knowledge about the integration with the complex arguments. And assuming that everybody has seen something like this with the residue calculus and things like that. So what we need now for t larger than t0, then we perform integration closing the lower half. I'm just setting this up here. Half plane. And then the contribution from the enclosed pole is going to give us just 1. So the contribution from the enclosed pole, the contrib from the enclosed pole gives just 1 here. So you can easily see that if you just reboot your memory. And hopefully your memory is not like mine. I have a goldfish memory and needs constant reboots. And then if you look at this function here for t less than t0, then you can close the contour in the upper half. But in the upper half, there is no pole. So that gives a 0 contribution. Then you would have a upper half plane. And there are no poles in that. Not Polish people, but poles in the propagators. Upper half gives 0 contribution. So that leaves a vanishing outcome since the pole is not included there. So at t equal t0, then the step function just jumps from 0 to 1. Then the step function, this is just some basic mathematics, the step function jumps from 0 to 1. And we know that the derivative, just to remind you of some of the basic mathematics of the step function, when t minus t0, this is equal to delta t minus t0 here. So if I now perform the Fourier transformation of the propagator, what I'm going to get then is the following. So I'm just going to set up the equation here when I perform the Fourier transformation of the Green's function, which we put up earlier, of g of r prime of t minus t0. This is going to give us Green's function, since we're only performing the Fourier transformation with respect to time. This is now going to give us an energy, and this is going to be equal to a sum over these overlaps, which we defined earlier, of r multiplied with a u of n of r prime, divided by E minus the exact energies, plus this I eta. And it's assumed that we take the limit, eta goes to 0. Now, one thing you see here is that clearly you will have poles or divergences here when E is equal to the exact energy epsilon n. Another thing which makes this equation not very practical is simply the fact that we have the dependence on the exact energies. So E, which you see here, could just be the energy which the particle has when it comes in. And you can actually calculate this Green's function for all energies. And this is equivalent as you calculating it for all times. So when we have performed that Fourier transformation, we can typically rewrite this now in the following way. And we are just going to do these rewrites before we take a small break. So this was nothing but the sum over n, and then we have these overlaps of r of n, and then n of r prime of 0, divided by E minus epsilon n plus I of eta. So remember again that these are the exact energies. It's common to rewrite this in the following way, 0. And then I have my A of R. This is a annihilation operator of 1 divided by E minus H plus I eta prime and dagger. So this should be a dagger here acting on 0. And this is often rewritten in the following way. Later, we are going to introduce this. This is not R prime. Like that. This is also called the resolvent. So this is just a rewrite of the Green's function. So in general, what we have now is a propagator, which if we have the exact energies, then the problem is solved. However, we do not have the exact energies. And that means that we need to do some approximations here. And we are now going to rewrite, after the break, we are going to rewrite these Green's functions as a perturbative series in the interaction. So then you will see immediately the link which pops up with the time evolution operator, which we had for time-dependent perturbation theory. And if we can sum all these terms to infinite order, we have the exact time evolution operator, or wave operator as we called it. In our case, the quantity which you see here is going to be a quantity which is similar to the wave operator, or this unitary transformation. And if we have this information here, in principle, then we can say everything about the system at any positions and at any times, or for any energies. So having the Green's function is a very powerful thing if we can actually solve it and have the exact one. But in general, we have to make approximations. So all of many-body theories is actually how do we make these approximations. And so what you will see is that the many-body perturbation theory is going to sneak in again, except that now we are going to have a formalism which allows us some very nice connections with the calculations of observables beyond the ground state energies and energies of the system. So let's take a small break. And then after the break, we are going to, and let me just introduce what we are going to do after the break. So we are going to use a relation between operators where we define a new operator, which is given by this energy E minus H0 plus I eta. And then I define a new operator B, which is, so E is just a constant, I times eta, also I is just the imaginary number and eta is a constant, and B is just H of I. So what we know is that H0 and H of I do not commute. So if you think of H of I containing the potential energy, we know that the potential energy and kinetic energies do not commute. So H of 0 could be, as an example, the simplest case, and that's one we are going to look at after the break. This could just be the kinetic energy. Kinetic energy. And then H of I could just be some kind of potential. It could be a one-body potential, it could be a two-body, or whatever we are looking at. And we know that the T and V do not commute. So there is a relation here. There is an operator relation, which is very useful and which you have seen before. So we can actually rewrite that in terms of, so these are two operators. So when this is the case, it means that A and B do also not commute. So this relation is a very useful one because it simply says that we can rewrite this in terms of these relations here of A minus B. So when we looked at Bruyère-Wigner perturbation theory, we could actually rewrite Bruyère-Wigner perturbation theory in terms of a compact operator relation. So after the break, we are going to use this one to find approximations we can make to the Green's function. So this is a very powerful operator relation, which you probably have seen in mathematics courses. You may have seen it. So we're not going to prove it, we're just going to use it, if that's okay. Have you seen this relation before? Okay, in another format. Okay, you've probably seen it because it's very much used, because if you take in quantum field theory, this is actually a relation which is used to set up the T matrix or the S matrix. Does that ring a bell? S matrix and T matrix? We're actually going to calculate after the break, we are going to set up the expressions for the non-relativistic T matrix. Yeah, yes, exactly. So all the machinery which you have seen in quantum field theory, you can transfer that directly to this case. And if you are taking away a medium, that means that you can have bound states. If you're just looking at scattering states, everything you have seen in particle physics. So all of physics is actually physics in the mediums. Particle physics is not physics in the medium, right? Because we are dealing with free particles in essence. Unless you're looking at quarks inside a proton or a neutron, or a baryon, or meson. So like nuclear physics is particle physics in the medium, because then we have both scattering states, I mean states in the continuum, and bound states, discrete states, because you have a potential which confines, an effective potential which confines the motion of the particles and can bind them. Whereas if you go to particle physics, is essentially free particles. Okay, should we take a small break, guys? So let's just bring. So what we are going to do now is actually to use this relation here. And what we are going to say now, if you look at the Green's function, we have the Green's function, which is given by 1 divided by E minus H0 minus H of I. This is the Hamiltonian which we had, plus this I of eta. You see now that if we use these definitions which we put up here for A and for B, what we have is nothing but A minus B here. And then what we are going to define now is a new quantity. So it means that if I look at this 1 over A, that is going to define the unperturbed Green's function. So I'm going to define a quantity which I will call for G0, which is simply 1 over A, and which is given by E. E is just a constant. So you're looking at the system. If your two particles are coming in with kinetic energy, this could be the incoming kinetic energy of the particles. And then we have an H0 here, plus this I of eta. Now with H0, what we are assuming is that this is a problem which we can solve, as we've seen before. So earlier we had that H0 had a specific basis as eigenbasis, and then we could expand everything in that eigenbasis. So G0 is now a quantity, a propagator, which we're going to assume plays the same role as H0 did in many-body perturbation theory or HCI theory when we expanded a new basis in terms of the eigenbasis of H0. So that means that when I look at the Green's function now, since I define G to be 1 over A minus B, and I can rewrite that as a 1 over A plus 1 over A times B and 1 over A minus B. And I'm going to simply plug in these definitions. So you see now that I can rewrite this as a G0, which is actually this term here. And then I have plus G0. And this is multiplied with my interaction piece. And then what I have next is actually the Green's function. So if you look at this one, this is nothing but my Green's function. So I can rewrite this in a very compact way, like multiplied with G. And now you see that this is something which looks like what we did earlier when it came to the wave function in many-body perturbation theory, or in Brillouin-Wigner perturbation theory, or Rayleigh-Schrödinger perturbation theory. So what we can do now is simply to expand this quantity here in G0. So we can rewrite this as G0 plus G0 of H of I multiplied with G0 plus, and then I get the G0 of H of I, G0, H of I multiplied with G0 plus plus plus, as we did when we set up many-body perturbation theory. And this means that also this G0, we are assuming that this is something we can calculate. So this would be something which looks like this, and an A alpha, a state, and then I have an E minus H0, and I'm not specifying these states alpha, these are just generic one-body states. And then I have an A beta of 0. And we would typically just write this as a function of alpha, beta, and E. Okay. So what we're going to do next is just to manipulate these equations here. And when we are now going to set up things, if we can write this in a more compact form. So if I look at the function G0, I can write this in a compact way, like an alpha of 1 divided by E minus H0 plus this I eta of beta. And similarly, my Green's function is actually given by the same thing, except that now we have in the propagator, we have H plus in the denominator, we have H instead of H0, like that. So I can then rewrite everything. If I'm now setting this up, when I use that expression, I can rewrite it as G0, which is alpha of 1 divided by E minus H0 plus I eta, state B, state beta, and then I have a sum of intermediate states, gamma and delta, and then I have an alpha, and then I have 1, this is E0 again, no, G0, not E0, but the G0, gamma, and then I have a gamma, and then I have H of I, and then I have a delta, and this is then multiplied with delta E minus H plus I eta and beta. Actually, if you go back to Brillouin-Wigner perturbation theory, you could have rewritten Brillouin-Wigner perturbation theory in a similar way. We discussed that briefly a little bit earlier. Now, what you see now is that if we look at this state, this G0, this is something which we then can compactify, because H0, if we now assume that H0 is has beta and alpha as an eigenbasis, if H0 has this as an eigenbasis, then we know that this is epsilon beta times beta. So if I then look at this expression here, this simply has to give us delta alpha beta divided by E minus epsilon alpha plus I of eta. So just keep in mind that we are still staying with a one-body problem, okay? So we haven't gone beyond the one-body problem. And this H is now a one-body operator, or it could be a two-body operator, but it acts on a one-body system. So everything we've been dealing with now is just the one-body Green's function. But this is something which we can extend easily to two-body problems and many-body problems. So the basic mathematics you see is not limited to one-body problems. But the states which I'm looking at here can be interpreted as one-body states. So if I look at the last term, this G0, we would represent that graphically in the following way. So G0 graphically or in terms of a diagram is pretty close to what we set up yesterday when we discussed the time-dependent version of Wick's theorem. So we would have a state beta, and we could think of this as a T2 if we wish to have time, but we have Fourier transform to energy. So there's an energy E, and then we end at a state alpha at the time T1. And we have assumed that T1 is larger or equal than T2. So this is just a compact way of representing G0 of alpha and beta with a given energy E, or a time difference T1 minus T2, if you prefer that. If you go back to time, keep in mind that we have Fourier transform to energy. If we look at the second order process, and this is something which brings us back to the expression which you see here, this one, we can represent that diagrammatically as well. So for the one body case, this would look like as follows. So let me just conclude the arrow here. So a second order term takes the following, has the following graphical representation. So we would start with a time T2 or given energy. So we have the same energy, but then we come to an intermediate state here, and then we have an interaction. So we move into a state delta. This leaves with a state gamma, and we have a final state alpha. So we begin with a beta, we end in an alpha, and then we have a time T1 here, but we have the same energy E. So you could keep time, or you can just keep this energy dependence. And this would be an example of a second order term. So where in principle, what we have done now is simply to sum over gamma delta, and then we have G0 of alpha and gamma for an energy E. This is multiplied with the interaction with a gamma of H of I over delta, multiplied with G of 0. So this should be an upper G of delta and beta at a given energy E. So this would be a second order term. And then depending obviously on interaction, whether this allows only for diagonal terms, then we would have a Kronecker delta for gamma and delta, but in general, we don't have that. Yeah.
Relation between E and the alpha and beta?
No, because this is the same energy. So it's the same. So the energy, this is the, because we have Fourier transformed here. So the energy, and it's also a final time. You have a final time T2 and not T1 and initial time T2. So you keep the same energy which propagates through the system. So this would be the way you would represent the second order term. So what we are going to do now is just some manipulations of this series expansions. And then we are going to define something which is called the T matrix or the scattering matrix. And some of you may have encountered that in quantum field theory. So what we do now is a simple reordering of the expressions. So if you look at the perturbative expansion we have for G in terms of the unperturbed case. So we have a G, and then we have this H of I, we have a G0, and then we have a G0, H of I, G0, H of I, G0, and then plus plus. This is something which I now can rewrite as a G0 plus a G0, and then I can rewrite that as an H1. And then I have a G0 plus a G0 H1. And remember now that these are infinite series. Okay? So that means that this goes also to infinity, this series which you have here. And this is something which I can now rewrite as the following. I can rewrite that if you now look at the expression which we have, this is easy to see now that I can rewrite this as a G0 plus G times H of I multiplied with G0. And I can rewrite this one as a G0 plus a G0 plus a G0 of H of I of G plus, and then I have H of I multiplied with G0. And this is nothing but G, so the way I see that is actually through this expression here. So this is this HG times H of I of G0. So the way I reached this one was simply to rewrite it like this. This again is something which I can manipulate in another way. So I can actually rewrite this one now if I do that, G0 plus G0, and then I have H of I plus H of I of G0 of H of I plus multiplied with G0. Now, what I'm going to do now is to define a quantity which becomes an effective interaction. And this effective interaction is called the T matrix. So this quantity, which you see in the brackets here, is now going to define a specific term, which we normally can solve numerically rather straightforwardly. So let's just rewrite this by defining the so-called T matrix. So not time ordering, but the T matrix. And you can think of this as an effective interaction, where we now are summing the interaction pieces to infinite order. So in an effective interaction, H of I, which we call for H of I tilde. So what we can do now is to actually redefine this T. If we look back at the equation which we have here, I can define my T matrix as this sequence here. And that looks very much like my interaction to given orders. So H of I plus H of I times G0 times H of I. And this goes to infinite order in the interaction. So that means that I can now rewrite my full my full Green's function in terms of a G0, which I can calculate, plus a G0 multiplied with this T matrix, which depends on energy, and G0. So if I can calculate this one exactly, which means often numerically, then I obviously have solved the problem because I know this quantity. And if we are representing this in terms of a discrete basis, then this is going to be a matrix. This will be a matrix. This is going to be a matrix, and that will be a matrix. And then we actually have just to perform matrix multiplications. So let's take a look at what this T matrix could look like. We can also rewrite this equation here. If you now look at this T matrix, so this is just a rewrite again. It's not that exciting, but we could actually rewrite this T matrix as an H of I plus an H of I multiplied with G0. And then I have an H of I plus H1 times G0 plus H of I, and then have times multiplied with H of I plus. And this is nothing but the term which is H of I plus H of I times this G0 multiplied with the T matrix. And I can actually rewrite this one. It's easy to see how you can rewrite it as H of I plus H of I times the Green's function, if somebody gives me that one, multiplied with H of I. These are just the different ways of rewriting these equations. So let's now look at an example. What we are assuming is that H0 is just the kinetic energy of a given particle. So that means that if I act with T on a state K, then I have K squared divided by 2m multiplied with K. And here I'm taking the liberty of using this particle physics notation with natural units. So I put these quantities to 1. Then I'm also going to set this h of I, and I'm going to put that one equal to a term v. So if I now look at my expression for this T matrix, so what I'm going to calculate now is a overlap for this T matrix, T of E, K2 here. And what I'm assuming is that there is no energy dependence in V. So this is what we normally call a local or non-local interaction, because it depends only on the spatial degrees of freedom. So no energy dependence means also no time dependence. So no E dependence here for the potential. So this is going to be, if I now use the expressions which I have, so my expression for the T matrix is this quantity which you see here, this one. So let's set it up, because I can actually rewrite it like this. So this is the expression I will be using now. So you see now I have H, there is a G here. So when setting up, it has to be in here. I would have to plug in a completeness relation for my propagator. So that means that what I'm going to have when I'm setting up, when I'm using this expression here for the T matrix, I will have the following. So it's going to contain K1, these are just two given states, times V, and K2 here. But then I have to plug in a completeness relation. So I have plus, and then I have an integral dk. And now I'm going to be a little bit sloppy. I'm going to assume that this is just in one dimension. And I'm going to skip a normalization factor of 2 pi. So I just leave out the 2 pi in the plane wave approximation here. So the eigenstates of kinetic energies are just plane waves. We know that, right? So I would have a dk, and then there is a k1. So I am now inserting this k here, and I have k here. So that will be my propagator, which now goes like E minus, and since I have H0, which is since this is the unperturbed Green's function, or G0, I have 2m plus I of eta, and then I have the T matrix and multiply with K2. So the quantity which you see here, this one, is nothing but my G0 term. And if we go back to the expression, this is a term which I'm plugging in here. I have the interaction here. Yes, and then I just put in the completeness relation, which I did here. And then I have to integrate off, because I'm using the completeness relation for momentum states of the particles which are not bound. So this is just a scattering state, or just a continuum of the states. And the energies are always positive because they're only kinetic energies, okay? So there are no bound states in this system. So you can think of this as the scattering of a free particle. If we are using this case as relative momenta, if we are looking at two-body scattering, in two-body scattering, you would have the same equation, but then you would typically transform your variables into the central mass frame. So then you would have, instead of momenta K1 and K2 for the two particles, you would have the relative momentum and the central mass momentum. And then it's common when you set up these equations, when you work in the central mass system, to put the central mass momentum to 0. And then you just deal with the relative degrees of freedom, yeah?
I'm a bit confused about which T is what there.
So T here this is the T matrix. So if you look back at this equation here,
also use T for the kinetic.
Yeah, you're right. That's a good point. So I should, yeah, I actually didn't think here. You're right. So I should actually say a kinetic energy. So let's just call this for an uppercase K here. Okay. That's a good point. I'm so used to use a T for kinetic energy. Or rather, what I could do, but then my handwriting, I could actually have something which looks like that. A tilde T, right?
The T in the last expression, that's the T matrix.
That's the T matrix. So let's just use T for T matrix and upper letter K, uppercase K for kinetic energy. Good point.
Okay, just to make sure in the integral, it's expectation value.
Yeah. Yeah. So this quantity here is a quantity which we often can calculate. And let me just show you how you can do that. Because this lends itself for a discretization. So when you do that numerical, so what I'm going to do now is just to have a small numerical digression. So let's do that. Because this is the way you would calculate the T matrix. So it's a quantity which, for free scattering, we can often calculate that one. So what we would do then is simply to start with our momenta, which are now given in principle from 0 to infinity. And we discretize. So what we get now is a discrete set of momenta. So we are performing some mapping. And when you do this numerically, the standard way is actually to use a technique which is called Gaussian quadrature. And some of you may have heard that if you took computational physics. So that's a pretty standard technique. So you would map, you would have a mapping which brings you from 0 to infinity to some specific value k0, which is often close to 0, and kn, which is then going to represent something close to infinity. This works well if you have a potential which dies off slowly. If you have a potential which varies a lot, even for large values of k, then this is a recipe which is not the best one to use. So what that means is that you can then replace ki of t, of the T matrix, in terms of a matrix Tij. You can do the same thing with the interaction V of Kj. So sorry, this should be V here. And then if I take the denominator here, this K and K, the denominator which has the energies of E minus this K squared divided by 2m plus I eta multiplied with a dk. This is something which we are going to replace with a diagonal matrix, djj, which is going to contain some weights, wj. These are integration weights, which follow the integration algorithm if you're doing Gaussian quadrature. And if you use Legendre polynomials, then you would have a specific set of weights. If you have other types of polynomials, you will have other types of weights. And this is going to be given by E minus this kj squared divided by 2m. Note now that you have an imaginary part. So you could use a principal value here to set up the real part and the imaginary part by themselves. So this is normally what is done. What I'm doing here is simply to set up the equations, and just keep in mind that you have an I times an eta, which also leads to a real part and an imaginary part. But we are not going to solve that here. But if you use these quantities, you can rewrite Tij as Vij plus a sum over k, and then you have Vik, then you have this matrix dkk multiplied with Tkj. That's the equation in a discretized form. So instead of integrating, you're now summing over the discretized momentum. And this is typically the way you solve this type of equations. Now, what happens then is that if you rewrite this in a matrix form, this is nothing but T is equal to matrix V plus matrix V times matrix D times matrix T. Now I'm taking all the indices I and J. So I'm just setting up this as a matrix. So T is a matrix, V is a matrix, D is a matrix, and T is a matrix. And that means that the only thing you need to do then, if you can invert that factor, you can actually invert 1 minus V times D times V. So if you can invert that matrix, and you obviously see that there are problems with poles here, you have to split it into an imaginary part and a real part. But these are all technicalities which you can deal with. So this is a pretty straightforward thing to deal with numerically. This is the way you would solve it if you have a problem which cannot be solved analytically. There are some simple analytical potentials which you can actually plug in and solve for. But in most cases, you would have to resort to a matrix inversion. You discretize, you set up these matrices, V and D, and then everything here is known. And that means that you can get your T matrix. And when you have the T matrix for this scattering problem, so this is actually a free particle or two free particles if you transfer into relative system of motion and center of mass, then you end up with an equation which you can solve either for the one body or the two body problem. So if you have a two body problem and you transform that one to the relative coordinates and the central mass coordinates, this is the same as you moving from a two body problem to a one body problem, because normally a potential which you have, like this interaction H, depends only on the relative distance. If there is a dependence on the central mass momentum, then you cannot separate the variables. But in effect, the effective part of this is that a two-body problem can be transformed into something which looks like a one-body problem. And this equation which you see here is something which you will see both for one-body problems and two-body problems. And this is a type of equations which can be solved numerically. And in some cases, you have analytical solutions even. Any questions so far? I just wanted to show you that the things we're dealing now with free particles are often things which we can solve either analytically or numerically. So what I wanted to do now is to start the discussions on how we solve these Green's functions problems, looking at Dyson's equation. And that's the basic recipe which is normally used in Green's function theory. And in order to do that, we are going to rewrite a little bit the single particle propagator, and we are going to use the Heisenberg picture in order to set up the creation and annihilation operators. So we are going to have a slight rewrite of these Green's functions. So what we will start with is our first steps towards Dyson's equations, which is one of the kind of practical recipes for solving the Green's function problem for more complicated interacting many particle systems. So we are going to prepare the steps towards Dyson's equation. So one of the things which we need is actually to assume that now we have an annihilation operator at time t, and we are going to use the Heisenberg picture. So this is the Heisenberg picture. And I will not have a subscript or superscript H to indicate that this is in the Heisenberg picture. This is given by E. Remember, we had this transformation, which we discussed yesterday and last week, of T times A alpha. So this is the normal one in the Schrödinger picture. And you can find all these expressions in the slides which I put online. So everything should be there. And then I have an e to the minus I of h, the Hamiltonian times time. And then I have a similar one for the creation operator, which is going to be given by e of divided by h of a of t. I realize that I'm not consistent in skipping h bar. So sometimes I keep it and sometimes I leave it out. I should be a little bit more consistent here. Then we're also assuming that this Hamiltonian acts on a given state psi 0, and that there is a, let's say, an exact ground state psi 0. In general, what we have is a psi of I is going to be given by some e of I times psi of I. And the state psi here can be a many-body state, or it can be a single particle state. So we haven't specified that yet, okay? So this psi 0 can be a ground state, can be a single particle state, single particle, or many-body state. So I'm just leaving that to the more specific cases, which we are going to look at. And then what we need next is this definition of the time order product, which we had last week. No, not last week, but yesterday. So we had, and now comes a new T here. And this is not the T matrix, but say time order product of creation and annihilation operators. So let me just write this, time ordered product. And we know that this one, when I put this T here, of alpha, of T, of A, of beta, of T prime, this is something which we defined yesterday as a T minus T prime. And this is for, the first one is for particle states. And then we have an AT of A beta. But then we have the part here which depends on the whole states. And then we have T minus T. So this would then be an A of beta of T prime times A of alpha at T. So the first part is for particles, and the second one is for holes. And we have the theta function as a way to implement the that the equations have to obey causality. So what we are going to do next then is actually to define this Green's function of alpha and beta before we perform the Fourier transformation to energy. This will be depend on these quantities. And this is going to be defined now as minus I divided by H. And then I have my psi 0. And then I have this time ordered product of A alpha and T of A beta dagger of T prime. Like that. And this is where we stop today, because now we are over time. And next week, we are going to look at these equations. You can find them in the slides. And then we are going to use these to define Dyson's equations, which is the standard recipe for solving the Green's function problem. And when you have the Green's functions, you can calculate observables like the energies. You can calculate spectral functions, which are very useful ones when we are looking at conservation rules and sum rules, etc., etc.